What up, Bingham Blazer?
What up?
We're gonna be dealing with phase changes today.
Sweet.
And we're gonna be changing from one state of matter to another. Another. Picka picka wah wah. Wicka wah.
Okay, that's enough. All right, so we're gonna look at water and how it changes states. So we're starting with ice. Ice is a what state? What state, boys?
Solid. It's a
Solid.
It's a solid, Mr. Schmidt. It's a solid.
Ice is a solid, okay? So we're going to heat this up and we're gonna see what state it becomes next after solid.
Ooh.
Okay, a lot of the times when we look at boiling point, we do look at water because as we all know, water's, sorry, I'm distracted.
Oh, water has a boiling point that we all know, and water also has a freezing point we all know. Now let's all in class right now scream out what water's boiling point is. Everybody at once.
Celsius.
In Celsius. 1, 2, 3.
100 degrees Celsius.
All right, now let's scream out the freezing in Celsius on the count of 3. 1, 2, 3.
0 degrees Celsius. I think it's 0.
All right, go ahead.
So when we look at,
All right, so we're gonna let this get closer to its melting point as it's going from a solid to a liquid.
Should we ever mix this with our fingers?
That would be bad, Mr.
okay,
Holly.
we won't do that
It's
then.
it's really warm. We don't
Yeah.
want to do that. We
Warm
want to
fat.
use a stir stick to do
A
that.
stir stick.
All right.
So we are going to add energy to that, heat energy, which is going to increase the molecular motion, the movement. And as that movement starts to motion, well, you'll see what'll happen in a second. We'll come back to that in a moment.
Let's look at some virtual motion while we're waiting for our time.
I love the virtual motion.
Virtual
You see
motion.
Okay.
Motion.
Right here we've got a molecule, what it would look like at a molecular level. These are the atoms. Over here we have what it would look like physically if you were staring at a beaker, like the beaker we started over there.
Oh.
And over here we're going to change the temperature, and of course we have it in Celsius. And earlier you yelled out what freezing and boiling would be, so here we go. We're actually below 0 right now, and as you can see, this represents it's frozen, ice solid. And over here our molecules are hardly, well, they're not moving at all, actually. They're just kind of hanging out. You can't punch through that right now because it would probably break your hand. It's solid.
That hurt.
We're going to slowly increase our temperature over here. Maybe. Now we're up to 0, which is still freezing, so you'll notice we still have a solid. Our molecules aren't moving. And as we gradually...
Oh, look, it changed.
Oh, crazy change. Our molecules are now in a liquid state. State's changed. We're starting to get movement. These molecules are not just touching and vibrating, but they're actually rolling and rotating around each other. I don't know what your teachers have already explained to you, and I know in 6th grade they had some matter already, but that's one of the signs of changes in matter. You go from that vibration thing to actually being able to move around the entire molecule.
So does this have the ability to flow?
Ooh, flow. That's nice. And we're not talking about that lady on that TV show.
Oh, yeah, we don't like her.
No. Okay, so we're going to heat up the temperature a little bit. We're going to go halfway up, halfway to boiling. So you'll notice over here we're starting to show some signs of boiling. Got some little bubble action coming out of there. We've heated up our flame. We're up to 50 degrees. And our liquid is now starting to bounce a little more crazy. Like they used to just be rotating around each other. Now they're actually starting to escape enough energy that these are escaping out the top.
So those molecules actually have more energy now?
Oh yeah, lots more energy. Before they weren't moving at all. They were frozen, state of solid. Now we're not only are we a liquid, but we're starting to create enough heat energy, enough movement that the pressure pushing down is actually not as strong as the movement trying to escape it. So we're getting those little bubble actions, and we're starting to get some actual evaporation at this point.
So is that why it looks like some of those circles are leaving the square?
Yes. Now it's important to remember that water will evaporate even at very cold temperatures. It just does it really, really slow. If you've ever put ice in the freezer before and left it in there for a really long time, what happens to an ice cube?
It gets smaller, doesn't
It's
it?
smaller. So even at that state where it's really, really cold, it can evaporate, lose molecules. Pretty cool.
That is pretty cool.
All right, so we're going to go up. Ooh, what's that sound?
Well, it sounds like a...
Okay. We're up to 90 now. We've added some heat. Oh, actually, we're at 81. Sorry, I can't read my scale over there. And once again, molecules are moving a little bit faster, and they're escaping because of their molecule movement. All right, we'll just keep going because, hey, we want to see this puppy
Yeah,
boil.
let's see what happens here.
Oh, look at that. We're at 100
Oh.
degrees. We've now changed from a liquid. Now we're saying it's a gas. Oh, check this out.
Dude,
It
it's
is going
gone.
away. It is going
Where's
away.
the water
It is going
going?
away. Bam! No more water. It's all in a gas state. So we've gone from a solid to a liquid to a gas. And those things are crazy moving around.
Yeah, they are.
Schmidt, it's turned to water!
It's water now.
Let's go back
Whoa.
to our other one. Let's go back to our other one. We'll lower this
Let's
down.
see our physical proof here. We have water.
Got a couple
So
floaters
you-
there.
Got a
A
couple
little bit of
floaters.
ice, but I see some bubbles
check out
starting.
this. This isn't what we're doing right now, but check out this stuff out here.
What is
what
that
would we
called?
call that? I know in 7th grade we do weather.
I
When
don't
we
know.
get liquid forming on the outside of a jar, we call that condensation.
Ooh, condensation. Does that mean that my glass is sweating?
Oh yeah, that's another. Well, yeah. If you're at home, that's probably what you've heard your parents say or someone say that your glass is sweating, and that's the reason why they always say, "Hey, put that on a coaster. You're gonna make a ring." Well, that water ring drops eventually down to the bottom because it forms the water beads, makes that little circle, and ticks off your parents when it leaves a big giant circle on their furniture. So that.
Condensation sounds a lot like evaporation. What is evaporation?
Well, evaporation, we saw that on the other board. These molecules are just going to slowly move their way out of that liquid form and form into a gas. And like I said, it doesn't even have to be cold to evaporate. Things can evaporate at room temperature. They can evaporate colder than room temperature.
So where's this water on the side actually coming from?
Well, you see, there's gas molecules out here. And if out here is a different temperature than in there, they actually want to stick to the jar and form that outside condensation. It doesn't actually come from inside, it comes from the vapor on the outside that gets attracted to that.
So that's like proof that whenever my teacher's been telling me that there is water and gas form out here, I can see the proof whenever it goes back to liquid form on
because
the
you
outside
can't-
of my glass.
Because you can't see the gas, but as soon as it turns back to a liquid, it shows proof there was a gas out there in the first place.
Sure was. And how come now that I'm getting really close here, I don't see any of that condensation now?
Over time, it's like when you're in your car sometimes and the windows fog over, but if you turn on your heater, it all goes away after a little bit. Well, our temperatures between the inside and the outside are starting to balance. And when they start to balance, condensation stops and it goes away basically. It starts going back out into the environment, not collecting on the actual glass itself.
Very interesting.
Pretty sweet.
So now we have like a graph to look at while we wait for one more phase
Yeah, let me
change.
switch this over here. Make sure I don't screw this up. Oh, I know. No.
No.
Okay, here is the phase change diagram. Now, if you've seen one of these before, this is nothing new. In a phase change, you always are adding heat. Now, that heat source could be through anything. We're using a hot plate. Could be regular fire, could be electric, whatever. And we're going to increase temperature because as you add heat, temperature goes up. Now, this, of course, is in degrees Celsius.
If I was a science teacher that liked to have really good labels, is this heat added on the bottom over time technically? Like I'm adding it over time?
Yeah, it is. And in just saying heat added, I don't really like that. I would like it to be more specific. But for this purpose, just to keep it, I guess they made it general just so you could talk about more than one liquid, but we're adding heat, and because it doesn't say what rate we're adding heat, because
yeah.
we could like blast furnace it and heat it up really quick, or we could heat it up really slow, and maybe they didn't want to get into that with this particular video clip. So I believe what we're looking at here, because we're at 0, this is 0 degrees Celsius, and we're at a solid. So that would tell me, if I'm looking at this and I'm analyzing this little chart going on, what do I know that's a solid that could turn into a liquid at 0 degrees?
Water?
Water. Or, I could just read it over here and say temperature of H2O. What H2O is H2O, 2 hydrogens, 1 oxygen, and we call that, in layman's terms, water.
Yes.
So we are talking about water. So anything 0 and below, we are in a solid state. Now, I don't know how much that you can see on the camera, but up here, these are those molecules again. They're solid. They're stuck together. So they make a solid. And they're vibrating a little bit, but they're not moving around. Now, at 0 degrees, we start to mix that. Now, I don't know if you've ever heard this before, especially 6th graders. This little delta sign means change. So we're adding a change of H for heat. And as we add heat, our molecules start to bounce around.
So this is like earlier whenever we had some floaties.
Yeah.
Oh, there's a little floaty there.
Yeah, like that, right before we were seeing that condensation, we were seeing floaties in there. That's a great example, Mr.
That's a
Schmidt.
great example.
So in this state where heat is being added, the temperature is remaining the same. because the molecules are starting to split up. And when we get to a point where all those things are now split up and turn into a complete liquid, our temperature will rise again. And I know I got a video clip of this somewhere else. I couldn't find it for today, but it shows how those in-between states, solid liquid and liquid gas, the temperature doesn't actually change. It's pretty cool.
Schmidt, we're losing water.
No way.
True, and there's bubbles.
Ooh, bubbles. Let's finish up this real quick.
Let's do.
We keep adding heat, and as we add heat, the temperature goes up. So this is a complete liquid state. So we're adding temperature, the heat is rising, and we're staying in this liquid state. Because we're getting excited, it's starting to get ready to boil. And then finally we get up to our magic 100 temperature, which we talked about earlier. It'll stay at that temperature and boil at 100 for a long time.
So that's probably what I'm experiencing over in the physical state right
hopefully
now.
that won't boil dry by the time we get back over there, but that's what's going to happen. Right now over there, we were just told that we're starting to get some bubbling, boiling action. So we're actually going to start some of that gas production. And that's what's happening right here. We have a liquid and a gas mix. So we got a little bit of gas getting excited, higher energy.
Oh yeah, they're moving around a lot.
Lower energy, and it's a mixture of the two. So we can still see the liquid in the jar, but we're getting gas to come out of it, and we're getting a mixture. And then finally, we get way over here and we can start to heat up again, and now all we have is gas molecules. The liquid's completely gone and we formed a lot of gas. Now I don't know if this is something you've heard before, but steam burns are the worst because steam is gas, and gas is at the highest
amount of energy.
Point of energy. So that's really the hottest stuff that can burn you. So when you're like cooking pasta or something, you have a lid on it and you pull the lid off, that steam that comes out is, well, smoking hot. It's not really smoking, but it's super hot because all that energy has been brought into that water. And it's not just water that's a liquid. It's so hot it's turned into a gas. And when it hits you, it's hot. It's probably over 100. And it can burn you pretty bad. So steam burns, ooh, yeah. Don't like those. They're not good.
This is a very cool graph.
Oh, I love this graph. It's awesome.
Let's head on over to our
Let's see how the
physical
experiment's going.
specimen.
Bubbling.
Oh, so we call this boiling.
Yeah, I mean, you can still obviously see there's a liquid in there. I'm not going to touch that because that's a lot of energy blowing around. And you can see the bubbles forming. And can you catch this up here? Can you see this? You
sure
can actually
can.
see, I don't know, does that help?
No, it doesn't.
Okay, you can see that steam rising in and forming that gas. Now, because we can see it, it's not really gas, but once it gets way out here, bang. Now, if you can't see anymore, it's a gas. You'll notice condensation starting to happen again, but this time, instead of the water being built up from the outside, that condensation's forming on the inside because that, as it comes up, is cooling off, and it's going from a gas as it's going up. It's cooling, which drops the phase, and it wants to turn back into a liquid. So that liquid is forming around the edge again.
Very cool. I want to see if I can get maybe a shot of that. Oh, look at how maybe my lens is... Oh, it's fogging up a little bit.
And I bet if you pulled that away a little bit for a little while and cooled it down, that fog would go away. But you can see, ouch, you can see how those water droplets on the inside of the glass form. They're cooling down, so they're reforming as a liquid and falling back in, heating back up, and coming back up.
So there's no liquid on the side here. I don't see it. It's all on the inside.
Yep, it's all on the inside because it's forming from the gas that we're creating on the inside of that beaker. You can, oh, right there, you see it? It was starting to fall down the edge. They'll form water droplets, go back down in the water, reheat, and go back out the top.
That is one of the coolest things I've ever seen.
The amazing things you can see while just boiling water. We should throw some pasta in that and make some noodles.
It is dinner time.
Ooh, I bet if we add an egg to those noodles, we could make, what is that when you put eggs with noodles?
Chinese?
Chinese. All right. So, I know that we wanted to end this in a spectacular fashion, and Mr. Schmidt had some amazing stuff that really has nothing to do with phase changes, but you do see some liquid in the end of this.
Oh, so all I got to go is drum roll, please. What up, Winston?
Liquid, gas. What up?
What up?
What up? And that guy, and this guy, what up?